Hello! Today we're going to look at how to build a synthesizer from first principles. I'm a musician, I play the guitar, but I'm not a trained musician by any means, nowhere near an expert. But being a programmer and being interested in music, I thought it's about time we have a go at trying to build a synthesizer. This will be a software synthesizer, and I know you can get them, but I think it will be an interesting learning exercise. I believe this will be a multi-part video. Today we're only really going to look at the basics of what is a sound wave and how do we represent that on a computer system, and I'm going to share with you some code that I've written which will allow you to play with these sound waves very easily. Single file of code you can pull into any project you like. Now, those intro themes that you heard me play there were Back to the Future and Godfather, and they were replicated using my PC keyboard as an input and a square wave for an output. Now, that might not mean anything to you right now, but by the end of this video you'll have a good understanding. I should say now that this video is really aimed at the beginner, perhaps both in sound synthesis and for programming, although I will throw in some programming tricks to make sure we've got the more advanced programmers to keep them on their toes. Let's start with the very basics. Here is a sine wave. You can think of a sine wave as being air moving backwards and forwards to generate sound. In fact, if you look at your loudspeaker, you know that the cone, you see it bouncing backwards and forwards. Imagine that here is when the speaker is switched off, the cone pushing out, going backwards, going forwards, going backwards, going forwards, going backwards. The more it goes in and out, the louder the sound will be, and that's called amplitude. So amplitude you can also think of in terms of volume, loudness. Professionals will measure amplitude in decibels. We're not going to touch that just yet, we're going to keep it very simple. Now, the basic formula for a sine wave is amplitude times sine of the frequency times time. The sine wave I've got on the screen here is not centered around 0, it's actually offset to 0.5 because I'm going to use this as a visualization tool, and it will make things a little bit clearer for us all to understand. And frequency is how many times we see a peak within a given time interval. So if I increase the frequency here, we can see we get more peaks. So let's take this time period here, 0 to 5. As I increase the frequency, we see more peaks, and as I decrease it, we see fewer. And I can change the amplitude. So remember, amplitude was loudness, and we're going from 0 to 1. I would just like to take this moment to point out how excellent this tool is. This is desmos.com, which is a free graphing and mathematical tool for educational purposes. Now, we'll understand frequency as being pitch. So higher frequencies are high notes and lower frequencies are low notes. And that's why really bassy sounds you hear really throaty, you see the speaker moving very slowly. In fact, sometimes you can see it, but in high frequencies you can't see it moving at all. So we know these low frequencies are bass and high frequencies are treble. All sound is made up of sine waves of different frequencies and amplitudes. And if we take sine waves of different frequencies and amplitudes and add them together, we can create interesting textures and different sounding instruments. So here's a little example of adding sine waves together. Now, the formula looks horrible, and I'm afraid if you don't like maths, then probably synthesis isn't for you, but the maths isn't too bad. Here we've got 3 sine wave equations with a fixed amplitude in this case, 0.5, 0.25 and 0.1, but we get to vary the frequency of each one of them. Now, by adjusting the sliders, we can take a frequency and we'll add another one to it. So if we had a very low frequency here, there we go, to a high frequency, and zoom out a little bit, that will have an interesting sound. And we can add a lower fundamental frequency to it, which is more dominant. This has the larger amplitude. And just by manipulating sine waves in this way, we can create all sounds. This project is really about coding a synthesizer. I will be sticking to the Microsoft Windows platform. That's because I've already written some code which interfaces with the sound hardware, and that's available to download below or from the onelonecoder.com website. To keep it simple, I'm going to create a Win32 console application. I'm going to call it Sound Synthesizer. And I want it to be an empty project because it generates lots of stuff I'm not going to use, and we'll keep it as a console project. So we're not going to bother with Windows GUIs or controls. Everything will be handled just at the command prompt. And this is a nice way to make it easy for people to learn. I like console programs because they're limited in their access and their abilities to display information. This focuses you to think really about what you're doing. Creating an empty project. So we'll create a source file, C++, and I'm going to call that one main. All of the code I'm going to include for download and in this video is written to be accessible. It's not written to be the most optimal or intelligent way to solve the problem. I'm learning about how to do synthesis as I'm producing this video, and I'm hoping that through learning myself, other people might try and avoid some problems that I encounter. So let's begin at the very beginning. We want some basic console activity. Now I will be using the standard library quite a bit, so I'm going to throw that in there just to keep my code simple. And we want an int main for our program start and a return to 0. Now, I mentioned before, we're going to be cheating a little bit. I've already written a file which will access the sound hardware for us. And you just have to take my word for it that this file does nothing other than present data to the sound card. The source code is available, please have a look. And we're using this as a starting point. I think in a future video I'll explain how this file works. But right now I think let's get stuck into actually generating some noise. I've already created a file which will talk to the hardware for us. Let's add that to the project. We add the existing item and it's called the one lone coder noisemaker.h, and we'll have a look at that very briefly, but really all it is doing is accessing the sound hardware, creating a thread in the background and presenting us with a hook to apply data to the sound card. I will explain all of that in detail in a future video. Right, I've created a short program here which lists all of the sound hardware available on the computer and creates an instance of a class called OLC Noisemaker called Sound. It's using the first device that it finds, which is usually your system's default sound device. I'm also going to now include some additional numbers, and we'll have a look at what these mean. So I want the sample rate to be 44,100. I want the number of channels to be 1. And I'm going to put in 2 magic mystery numbers for now into the end here. You'll see there actually are default numbers provided by this class, so feel free to use it without making these modifications. So why is Noisemaker using a short here in angle brackets, and what is the sample rate and what does it mean? Well, let's have a look back at our Desmos powered graph. I'll take the original waveform off there and bring back our existing waveform. We need to represent this waveform as smoothly as possible. And a computer can't do that. A computer will only be able to store numbers digitally to a fixed amount of precision. And we can emulate this by applying a second function here. Now, I won't go into what this function is doing just yet, but it's a nice way of visualizing what happens as we apply more bits to represent the numbers that represent the sine wave. So as we increase the number of bits, we can see that the approximation to the sine wave becomes more and more accurate. So with this sine wave and 1 bit, you really only get a choice of top, bottom, top, bottom, top, bottom, because you've got 1 bit. It can be on, off, on, off. If we have 2 bits, we can see there are now 4 states in between. We've got bottom, we've got about 1/3 of the way up, 2/3 of the way up, and the top. And so on, and as we increase the number of bits, we increase the accuracy of the representation. So let's take 8 bits, commonly known as 1 byte, and zoom in. So now we've got about 256 levels to represent the sine wave. We can see we can zoom in quite a bit, but it's still an approximation. Now a short is 16 bits. Now you can see we need still a lot more zooming to get in. Still an approximation, but our accuracy is now quite high. The number of bits, in this case a 16 bit short, is really used to store the accuracy of the amplitude. The sample rate, the 44,100, is really used to store the accuracy of the frequency. Now, according to Nyquist, we need a sample rate which is double the highest frequency we want to record in our sound synthesis. Now, human hearing range that is about 20 Hz to 20,000 Hz. So 44,100 is a little bit more than double 20,000 Hz, which means we should be able to, in the most extreme cases, capture with some accuracy a 20,000 Hz or 20 kHz signal. Now, the nice thing about this piece of code is we can of course change our short to a char and it becomes an 8-bit system, or we could change it to an int which becomes a 32-bit system for audiophiles only. 16-bit at 44,100 is a common setup for most sound synthesis. The number of channels here is, do we have a stereo system or not? And in this case, no we don't. We'll worry about that later on, different video. Right now it's just going to assume we've got one speaker attached to the system. The 8 and the 512 here are used as part of latency management. And when we explore how the noisemaker utility works, this will become very apparent. But ultimately, we're trying to reduce the delay between hitting a key on the keyboard and hearing the sound. But if we don't give the sound hardware enough memory, which is effectively what these two numbers are defining, it gets starved of noise to make. So it's a balancing act, and we'll find ways to tune that in the future. So let's carry on writing our program. Now we've created the hardware and we've set it up. We want to create a function which allows us to play with the shape of the waveform, i.e. where do we put the mathematics. So let's create a little function up here, and we'll call it make noise. And it's important that the function takes a double type argument of dtime. The noisemaker class does everything using doubles, simply because they're easy for people to understand and they look simple on the screen. In reality, sound hardware on a software machine does everything using integers. We'll worry about that some other time, but like I said at the start of this video, let's keep this simple. So we're going to make the noise double D time. Now, double D time is the time that has passed since the start of the program. And we'll put in a sine wave. So let's remember our sine, and let's pick a frequency. Now, I'm not just picking a frequency here at random, I'm picking 440 Hertz, which is an A4 on a keyboard. You can Wikipedia why that's the case, but for now we'll say 440 Hertz. And effectively we times that by D time. So here we've got a frequency of 440 Hertz and an amplitude of 0.5, and it's a sine wave. There is one more thing we need to do though, and that is a little numerical trick, because this is a frequency in Hertz and sine doesn't really take Hertz, it takes angular velocity, so we just need to do a conversion. But that's simple enough, that just becomes 2 times pi. And we return all of that, put a semicolon at the end, we return all of that as at the given point of time that is supplied to us, what should our sine wave look like? Now we need to link that function with the noisemaker class. So this is simply a case of using a function pointer The noisemaker class is constantly running in the background, so this dtime variable that goes into our makeNoise function will be constantly increasing. It's up to us what maths we do, but we need to return a value between 0 and 1 to represent where the speaker cone should be. If you remember going back before, it's the amplitude of where our speaker should be relative to the time. And we've just created a simple sine wave function here. We should be able to listen to it, and it should be the note A. To make sure that the program doesn't just stop straight away, I'm going to throw in a little dirty while loop here just to keep it running. We're still at the debugging and learning stage, so calm down. But there's one more thing we need to add, and that is to our project properties we need to include the winmm.lib library. And that's because the noisemaker class in the background uses functions from that library. So let's try compiling. We've succeeded, and do we get a noise? And there we go. That's a sine wave playing in the background. Sorry if it's just bust your speakers. So we'll stop there. Now we can make some changes to the nature of the mathematics and listen to the differences. So let's start by doubling the frequency. So we'll take our 440 and change it to 880. It's higher pitched. Let's take that the other way to 220. It's lower pitched. So changing the frequency element changes the pitch. Sine waves are nice, but they sound a bit mellow, and I think they're a little bit dull. Instead of sine, we can use other functions, but they need to be periodic. Commonly used are the square and triangle wave functions. So let's have a look at how we can generate a square and a triangle wave. The easiest way to generate a square wave is to threshold a sine wave around its middle. So in this case, when we go over 0.5, we want to set the value to 1, and when we go below 0.5, we want to set the value to 0. Now we can see what this looks like. So in this case, we can see as soon as the sine wave crosses 0.5 here in amplitude, it actually goes up to a full 1. And when it goes below 0.5, it goes back down to the 0. And it will do this irrespective of the frequency. So as we increase the frequency, we see that the square wave bunches up, and as we decrease the frequency, it spaces back out. Let's modify our make noise function to turn our sine wave into a square wave. I'm going to create a temporary variable here which just captures the sine wave. And I'm going to modify it the output is greater than 0, return 0.3, else return minus 0.3. And we can get rid of this now. So this will take our sine wave function here, which I should get rid of this 0.3 now, so we have a full amplitude sine wave, and because we can only have either plus or a minus in a square wave, we set the amplitude explicitly. So let's have a listen. Now that was much louder, so I'm going to reduce that, and we'll probably discuss the power of a signal later on. There we go, that's better. And that's really cool because it sounds sort of retro-y, chip-tuney, 8-bit sound. And it's not surprising because the older games consoles and machines only had limited sound functionality such as toggling a pin up and down. Our program is becoming a little unwieldy now, as it just produces sound when it starts and we have to terminate it to stop. So let's add some rudimentary control. So I want it so when I press the A key we hear the note, and when I release the A key we don't hear the note. And I'm going to do this using a Windows function get async key state, which allows us to see what the state of any key is on the keyboard. And in this case I know that the A key can be represented using the character A. And basically I'm testing it to see is the highest bit of that key there. If it is, then the key is pressed, and if it isn't, then the key is released. So if the key is pressed, we want to specify a frequency to be played. So let's throw up here a variable. So we'll have a double D frequency, spell that right, frequency output equals 0, and we're going to use U as our frequency. So this is now a global variable. Now we need to be careful because D-frequency output is modified by this thread in the while loop, but the noisemaker runs a thread of its own in the background, which calls the make noise function. So just in case, we're going to make this atomic. If the key is pressed, we want our frequency output to be 440 Hz. Else, if it's not pressed, we'll set the frequency output to be 0 Hz. We've now got some rudimentary control over our sound, a little less annoying now. Well, we can extend this idea to implement a full keyboard. I've added some additional code here. I've taken the octave bass frequency. So before we did 440 Hz. Well, if I halve that and halve it again, I get 110, and that means I've gone down 2 octaves. So every doubling in frequency moves you up 1 octave. Now, in the conventional Western scale, there are 12 notes per octave. I can't just divide up the frequency difference by 12 because it doubles each time. So I'm going to use the power of 2 here to the 12th root. So that divides it up into our 12 notes, and we're going to use this to modify our bass frequency here with the note that we want. So for example, let's play this. Press our A key. That's a nice low frequency A. If I want to move up 1 semitone now, and I press the A key, we can see it's a bit higher. And indeed, if I move up the full 12 semitones of an octave, it's an octave higher than the original note that we played before. Let's take our basic on-off switch here and turn it into a piano-like keyboard. Right, I'm going to leave this little bit of magic here for as a bit of a mental exercise for you, but it's not that difficult to work out what's going on. I have effectively mapped the keyboard keys to the piano keys in the way that Z here would be A, S would be A sharp, X would be B, C would be C, F would be C sharp, V would be D, G would be D sharp, B would be E, N would be F, J would be J sharp, J would be J sharp. Oh, flipping heck. Anyway, what I'm trying to get to is it actually models out the white and black keys on a piano, and we've got these crazy characters in here. They're for the comma and the full stop keys to keep it going, and it basically tests each of these keys one by one and creates the frequency to output. If no keys are pressed at all, then our frequency output becomes 0. So let's give that a whirl. So I'm going to press the lower A, sorry, the press middle C effectively. So C, C sharp, D, D sharp, E, and so we have a basic square wave instrument now, which sounds pretty cool. Let's just change that back to sine waves for the time being. So in this case, we'll just turn the output, and I just want to reduce the volume a little bit, or else it'll get very loud. Ooh, 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 it's a bit scratchy. So we can hear that the timbre of the instruments has changed. It's not a square wave anymore. But we get lots of little pops and clicks and scratches, and if we hold down 2 keys, woof, yeah, that's really bad. So what's really happening here? Let's quickly sketch up an axis and see what it means for our sine wave. So let me get it in the right place. So let's plot here. We've got our amplitude and time. And if we choose a different colour for our sine wave, as our sine wave starts and it becomes a sine wave for a little bit, and then we switch it off. Well, instead of carrying on being a nice sine wave, what we've actually got is a vertical stop. Well, if we remember at the start of the video, the up and down movement of the sine wave is reflected by the in and out movement of the speaker cone, and we're asking the speaker cone to effectively, in one time period, be in 2 places at once. It can't do that, so it has to violently react, and that is what the click and the pop is that we hear. Likewise, our function could be at any point in time, so we might unfortunately start our sine wave down here and carry on, and the same situation applies, whereas we should have had a nice sine wave gradient so the speaker can accommodate that and produce the frequency. What we actually get is a very harsh crack and a pop, and this is actually a very high frequency, but because it's so high and so violent, the speaker cone can behave in unusual ways, so you'll get different sounds. Now you might be asking, why did we not hear that with our square wave? Why did we not hear clicks and pops? Well, that's because the square wave is, believe it or not, square. In fact, it relies on being nothing but a collection of clicks and pops. That's also why we had different volume issues with the square wave too. We're almost finished now, but before we finish this part of the video series, let's play with the sound one more time. We're going to make it sound like a chord. To make a chord, we simply add sine waves. So I'm going to take this function and add another. But I'm going to change the frequency slightly. I'm going to cheat, and for every base frequency that we get, I'm also going to offset it by another 20 Hertz. And I want to make sure that our amplitude is applied to everything. There we go. What does that sound like? It's an instrument. It's not the prettiest sound I've ever heard, but I know that for me, putting together this video has been a very educational experience. I've had to learn about sine waves, I've had to learn about synthesis, and I hope to improve my virtual synthesis instrument further, and we'll see that over the coming videos. If you found this in any way useful, please leave a comment below, and if you've got any suggestions for what we might want to do with the synthesizer, also I'd be keen to hear them. Thanks, and I'll see you in the next video.